Video presents a novel distributed approach for solving the inverse problem of a differentiable dynamic game, which enables robots to learn multi-robot coordination from given demonstrations. We test 4 different scenarios. In each scenario, we will first test the inverse game where each robot learns the objective from the given demonstrations, and validate the learned objective functions in a different environment for generalization. In the first scenario, 3 robots start from initial position to initialize the linear-like formation as a goal position while avoiding obstacles. In the second scenario, 3 robots cooperatively transport a suspend payload. The third scenario is a formation control with heterogeneous robots. The last scenario is a fixed swapping task for multi-robot system. We compare the computational scalability of the proposed method with the inverse KKT algorithm and the centralized inverse reinforcement learning method, which shows the efficiency of the proposed method for solving the inverse learning of a distributed differentiable dynamic game.
This paper studies a new framework for bi-level coordination learning. We are interested in MDP problems that have multiple but decomposable actions. We split them into 2. Action X for state transitions. Both action X and Y affect rewards. Under local observations, BiCL utilizes reinforcement learning for the policies of action X and imitation learning for Y actions, combined with an optimization. We also integrate the alignment penalty to minimize the mismatch between 2 levels. We apply BiCL to the raw-based environment. Here, robot positions are their states, and their velocities represent action X for state transitions. Y action is guard, a discrete action to choose which adversary to guard. Both X and Y affect reward. In graph-based, the node where robot locates are the states. Move is a discrete action to an adjacent neighboring node, which also induces the state transition. Guard is the set of edges visualized by green arrows. Both X and Y affect reward. In both cases, we show the efficiency of BiCL compared with other baselines. This paper focuses on learning coordinating maneuver in adversarial environments. Robots suffer risk in adversaries. They have the action for move and serve as the guard to reduce risk, lower speed, better guard. We also consider team task completion time. The goal is to minimize team costs, including a booth. However, it's difficult to solve due to the coupling relationships between team behaviors and time. To solve this, we propose a reinforcement learning with a special multi-weighted hard encoding and a reward reshaping mechanism. We simulated 3 environments and observed a bounding overwatch behavior. Robot move while some guard at the boundary. In results, for the bottom figures, x-axis represent time, y-axis represent robots' positions, and the color of dots represent the adversary they are guarding against. In a complex environment, similar as previous coordination pattern, some robots will sacrifice themselves to reduce the overall team cost.